sort of said that the previous video was going to be the last, and that was the plan. But I received quite a lot of questions about this specific exercise here by email, and I figured that rather than type out answers to emails individually, or for that matter, make a written post on Blackboard, I would go through this exercise because I think a visual explanation is a bit easier when I can point things out with the cursor. So essentially what we're asked here is, or we're given here a phenotype phase plane with a couple of other plots, and then we're asked to figure out what is the line of optimality. And a lot of questions that I've gotten also revolve around how do we actually read all this data and how can we get the information out from it. So as a reminder, essentially when we're looking at a phenotype phase plane, we can find four different things. We can find what's called an infeasible state, or an infeasible phase, where the model can't grow. Whether it has a growth of 0 or no feasible solution, those count as the same. And that will correspond to something like this green flat region here, right? Then, in addition to that, we have a single substrate limitation, double for substrate limitation, and the futile phase. And the classification of each phase, say, of any of these four into either category is defined by the shadow prices in each axis. And the relationship between the shadow prices will determine essentially the orientation of the plane. So a plane is essentially any given region where the ratio between two shadow prices is constant, and that normally means that both shadow prices are constant as well. And sometimes you can sort of see things off the straight three-dimensional phenotype phase plane like this, but that is not always the case. So in this specific exercise, trying to classify these four phases here, the blue, green, orange, and red phases, into the different types, you're not going to realistically be able to do that just based on this top left corner, or top left graph alone. So to do that, we've given three other charts here that can be helpful. Now, essentially what we're looking for is, so a single substrate limitation involves one shadow price being positive, meaning that increased access to that metabolite will increase the biomass production, and the other substrate being, and the shadow price for the other substrate being 0. And so that would correspond essentially to a plane that is slanted but only in one direction. That is sort of it's at an angle in the space, but it's going to be parallel with one of the axes, like either the x or the y axis, or with the x axis or the y axis. Now, a double substrate limitation, then we have both the shadow prices being positive. That means that adding either of any substrate will increase biomass production. Lastly, the futile phase is where at least one of the shadow prices is negative. That means that adding more of either metabolite will actually lead to a reduction in growth. And now the question is, how do we read out shadow prices? If we look at MATLAB, or if we go into MATLAB and we compute the phenotype phase plane using the function there, we will normally get we'll get something that corresponds to this upper left graph, and then we will also get a plot where, or two 2D plots with the shadow price for each metabolite at each point. We don't have that here, because with that we could have just read out for each region and figure it out from there. That's actually something I go through in the exam session that I posted earlier, in the exam session 6. But we don't have that here. Instead, what we have is we have this lower left plot here, which is the same as the top left, just seen from straight above. And then we have these two right plots here. And the question is, what do these plots correspond to, these two right plots? Well, they're the growth rate relative to glucose uptake. And if you look at the caption, when the O2 uptake rate is fixed at 5 millimoles per gram dry weight per hour. And so, and if we look at this bottom right, it's the same thing, but inverse, where we look at the growth relative to oxygen uptake for glucose uptake fixed at 5 millimole per gram per dry weight per hour. So essentially, if we change our perspectives, if we were to take this, if we look at this bottom left here, we can follow this line out from, say, if here the y-axis is the oxygen uptake. If we start at 5 and draw a horizontal line here, that will be the same as drawing over the surface of this phenotype phase plane. And as we move along an increase in glucose, we're going to hit these different phases, and our curve will go up and maybe down along this line. And that is what we see here. So for instance, if we look here at this first here, the sort of like crack or like bend in our curve, that is the transition into our first phase. That is, if we look here at 5, we actually start at, we actually have, this is a bit strange because we do have non-zero growth on the green here, which should be infeasible. But we see that from 5 to about, or maybe a half to 1, that is maybe this region here, right? So maybe this is just a matter of we have very few points and some numerical errors. But what we see here is each change in the slope of this point here corresponds to a change between the phase planes. And so this curve here essentially goes over all these 4 phases. We see that this one here goes all the way up to 20, which is further than this axis here brings us. So for instance, if we look at this transition here between orange and red at 5 oxygen uptake and 10 glucose uptake, that is this point here, roughly, and that corresponds roughly to this point here in our top right curve. Which means that we catch actually all our phases are shown on this graph. And since we see that this curve here is strictly increasing over the whole, over our whole interval, that means that the shadow price for glucose for all of our phases is positive. Now, if we look at the same thing for oxygen, well, then we're doing the same thing just along the other axis, right? So this line here, that increase and decreases, is what we get if we fix our glucose at 5, so that's this point here, and then draw a line straight up through our various phases. And then we see here that we have a bit of a bend at like somewhere over 6. If we look here, that is this interface between between green and orange. Because we see here the interface between green and orange is at for a glucose uptake of 5 is an oxygen uptake of about 6, which fits more or less with what we see in this slight bend here. We actually see that we don't see any clear bend that corresponds to the break between orange and red, and that is because the shadow price for oxygen is constant over these 2 phases. These are different, but the phases are still different because the shadow price for glucose is different between them. So we then see that this region here corresponds to both our green and orange, no, sorry, red and orange phases. Then this slightly slower but still increasing curve here corresponds to our green phase. And then if we look here at just after 10, we actually, an increased oxygen uptake leads to a reduction in growth rate. And that is, if we look here at 5, 5 to 10, that's this point here, which roughly corresponds to this summit. And this downward curve then corresponds to the segment of this line here of constant glucose uptake equals 5. That's in the blue phase, and that corresponds to a negative shadow price for oxygen, because this here is negative. And so with that, now we have a futile phase in this blue region, because one of our shadow prices is negative. That's this one here, and the other is positive. Not that that matters, but at least one of our shadow prices is negative. So this blue one here is a futile phase. Now, strictly speaking, that is not what this exercise asks, but a lot of people were wondering how to read this kind of data, and so I felt like explaining how we actually figure out the phases from a visualization like this is actually possible. Now, if we want to answer the question itself, we see that we're asked, what is the line of optimality? Well, the line of optimality is the line that corresponds to optimal utilization of a carbon source. So essentially, we want to see that for a given carbon source, for a given uptake of a certain carbon source, what is the highest, what oxygen uptake corresponds to the highest growth. And we see here clearly that for a glucose uptake of 5, so our line of optimality is going to be one of these phase boundaries. So the question is, which one is it? And well, if we can identify one point that that is on the line of optimality, then whatever line that point is located on will be the line of optimality. And if we'll look at our bottom right plot here, since the line of optimality is where is the level of oxygen uptake that gives the highest growth for a given uptake of carbon, then this summit here is on the line of optimality. And so since this summit here is, again, glucose uptake fixed at 5, as described in the caption, and oxygen uptake at slightly over 10, as we can read from our axes, that is 5, 10, and that is, again, this point here, which we see is on the line B. And so with that, we can conclude that B is, in fact, the line of optimality. I hope this has been helpful. I'm not quite sure if this is how clear this is, but I think trying to explain this visually is a bit better than simply going through the through an explanation in text.